Analyzing graphs of functions. The first part will talk about finding the x and y intercepts. We will find it algebraically, thus let's go to the following example. Find the xy intercept for the example in front of you. Start, let f of x equal y. The function will look like y equal x squared minus 4x plus 4. To find y-intercept, you always let x equal 0. Thus 0 squared minus 4 times 0 plus 4, the answer will be 4. Thus my y-intercept will be at 4, y equal 4. Now, to find the x-intercept, we have to replace y equal 0. In this case, you will have a quadratic equation, x squared minus 4x plus 4 equals 0. You have the blessing of the calculator, thus go ahead and use it to find the x's. Use mod 53. Now when you use it, the calculator will give you two values, and they will be the x-intercept. It will be at x equal 2 and x equal, it's only x equal 2. We have one x-intercepts, to be honest. Again, we need to find the xy intercept for below function. First of all, to find y-intercept, we will replace each x by 0. Thus, the function will be 3 times 0 plus 4y equal 9. Then we will have 4y equal 9, and accordingly, y-intercept is 9 divided by 4. Now, to find the x-intercept, you do the opposite, meaning y equals 0. Thus, the question will be 3x plus 4 times 0 equal 9. You end up 3x equal 9, and your x will be 3. We repeat again the same idea with the following function. Again, to find the y-intercept, put please x equals 0. Thus, the question will be 0 minus 2 times 0 squared plus 3. Accordingly, your y-intercept is y equal 3. To find x-intercept, you will let the equation equal 0, and you will rearrange it. Thus, it's going to be minus 2x squared plus 1x plus 3 equals 0. You will use mod 53 in your calculator, and the calculator will give you the values of x, and you will take them as an x-intercepts as illustrated in front of you. How to find xy-intercept graphically? First of all, you need to know what is the meaning of an x-intercept or y-intercept in any graph. When you say y-intercept, it is the place where the graph, the black graph, will cut the y-axis exactly. This is what we call y-intercept. You can see it as illustrated in front of you. Also, the x-intercept, it is where the place the black graph will cut the x-axis. In this case, you have 3 x-intercepts. Take the following graph. We can see that the function cut the x-axis at the point 1, 0, thus my x-intercept x equal 1, and cut the y-axis at the point 0, negative 1, thus my y-intercept is negative 1. In the graph in front of you, if he is asking you for the y-intercept, you can see the red graph cut the y-axis at the point 3. Thus my y-intercept equal 3. The same graph, the red graph, do not touch, doesn't cut also the x-axis. Thus we can say we don't have x-intercept. Odd versus even functions. The first type to decide is by checking the graph. Okay, even function. How to decide this is an even function? It is when you have the reflection on the y-axis. If the mirror in front of you, if you feel there is a mirror at the y-axis, then it means it's an even function. Check the two graphs in front of you. In case of odd functions, the reflection should happen at the point 0, 0 or the origin. Thus you need to have the feeling that there is a mirror or some kind of reflection at the point 0, 0, and then we will say it's odd as illustrated in front of you. Sometimes you go to not even, not odd function, or we say neither. Now, in this case, if you have the feeling that the mirror is the x-axis, then I assure you, basically, it's not a function, and you cannot say it's even or odd. It's not even, not odd function. Now, deciding given functions are odd or even by algebraical way. There are two tests. The first test is when f negative x equal f of x, we will say it's even. F negative x equal minus f of x, it's an odd. This starts with the following example. Decide if the below function is odd, even, or neither. Thus f of x equal absolute value of x minus 6. Now, in place of x, we will put negative x. And we will keep in mind that we are dealing with an absolute value function. Thus, absolute of negative x will convert it back to positive x. Thus, you will start with f of negative x, but you will end up going back to the original equation. So it's an even function. Another example, decide the following function if it's odd or even. Now, we place each x by negative x. Thus, the f of negative x will be negative x divided by negative x squared plus 4. We keep in mind that negative x squared is basically x squared. Thus, we end up, after simplification, having f of negative x to be negative x divided by x squared plus 4, and this is minus f of x. Thus, I can assure you this is an odd function. In the third example, to test if you are dealing with an odd or even function, replace again each x by negative x. Thus, f of negative x will be negative 3, negative x cubed plus 2 times negative x. You keep in mind that when you raise negative x to the power 3, it will remain negative x cubed, and you will work based on that. After simplification, the function will be 3x cubed minus 2x, and it's not f of x. Thus, it's not even. Now, we will try another trick. We will try to take negative from the whole function. And we will say, okay, if I took negative outside, I will end up negative 3x squared plus 2x. And yes, it is negative f of x. This is an odd function. We're back to deal with an odd function. One more last example. F of negative x will be negative x cubed plus negative x squared plus 3. We keep the negative with x cubed, but it will vanish with negative x squared. We go back and we replace everything. Thus, f of negative x will be negative x cubed plus x squared plus 3, and this is not f of x. Thus, I can say it's not even. Now, we do the same trick. Let us take negative outside this expression. Thus, negative is outside, and we have a bracket. Thus, it's gonna be x cubed minus x squared plus minus 3. And if you notice, it's not even negative f of x. Thus, again, this is not odd. This function is not odd, not even. We will go to the next section, and it's the extremes, dealing with minimum and maximum values. As an introduction, I want you to see the following function, and I want you to recognize that at A we have maximum, at 0 we have maximum, at value B we have minimum, and at value C we have another minimum. Now, we will say that at value 0 we have an absolute maximum, this is the biggest, and at value A it's a local maximum, it's not the biggest. And at value B, local minimum, it's minimum, but not the most minimum. And at value C, we will say absolute minimum. This is the idea of the lesson. Write also a note that you can use the value of absolute maximum or minimum treated to be local at the same, but you're not allowed to use a local minimum or maximum to be treated as an absolute value. Take the following example. You are asked to find the extremes for the following graph. We can see that at the point -3, 2, there is maximum, so 0.21. At the point -1 and -3, we have minimum, and so 0.4, -1. Now, we look at the graph. We can say we have local maximum, those 2 points, and local minimums. But since the graph at the both sides go forever up and forever down, there is no absolute there is no absolute maximum, no absolute minimum. I always advise my students to take notes on the graph, decide the maximum and minimum values, and check the sides of the graph if you have arrows, if it's going up forever or going down forever. This is an example of a limited function. It has a certain interval. You can see that I decided the minimum value and the maximum values. Then I start comparing. The maximum among all of them, which is 0.1-6, will be absolute. Minimum among all of them, there are 2 points which are 3,1 and -1, 1. They are treated as both local and absolute minimum. Coming sections, we will deal with the asymptotes, and I'd love to call them the danger zones in any function. Take the following example. You've been asked to find the vertical asymptotes, and they are in general the problems in the domain or the problems in the values of x. Let's start with the following example. Find the vertical asymptote for f of x equal x squared plus 5x plus 6. And this is a polynomial. And you know what? Polynomials are peaceful functions. Polynomials are great functions. Thus, there are no vertical asymptote at all. Another example, we need to find the vertical asymptote for the given y. Now, first of all, make sure that the denominator or the lower part equals 0 of any fraction. Thus, if you solve it, you will have x equal 1. This is a vertical asymptote in this case. A third example, find the vertical asymptote for y equal x minus 4 over x squared minus 16. First of all, we take the denominator or the lower part to be equal 0. We use the calculator, we factor it, and we end up having two values, x equal 4 and x equal -4. Now, because I have two values, there is a possibility that there is some kind of simplification in the future. Thus, I will write the function in a factor form, meaning y will become y equal x minus 4 divided by x minus 4, x plus 4. Like I'm taking each factor and I'm changing the sign of it and insert it in a factor. I'm writing each root in a factor form. Now you will notice that you have the same bracket in the numerator and the denominator, in the upper and lower part. Thus you will remove this part. Now removing x minus 4 will say that you have basically removed x equal 4. And you will say, okay, x equal 4 is a removable discontinuity. We'll talk about it later. Now, the simplest shape will be 1 over x plus 4, meaning you will have forever a problem at x plus 4 equals 0, which is x equal -4. This is why we will say only x equal -4 will be the vertical asymptote. Already you got rid of x equal 4 when you removed it. We're going to another type of asymptotes, which is the horizontal asymptotes, and they are the problems in the y values, and they will affect the range. Now, we have three cases to find the horizontal asymptote. Let us look at the function in front of you. 7 to the 7x divided by x cubed plus x minus 1. The highest power in the numerator, or the degree, is 1. The degree in the lower part is 3. Now, in the case of degree top less than degree bottom, you will say the following. The horizontal asymptote will be always y equals 0. This is the first case. Another example, give the horizontal asymptote for the following function: y equal 5x to the power 7 plus 1 divided by x to the power 10 plus x to the power 9. The degree at the top in numerator is 7. The degree at the lower part, or the denominator, is 10. Again, we have degree top less than degree bottom. Thus, the horizontal asymptote will be always y equals 0. And y equals 0, by the way, has another name, which is x-axis. Now I'm moving to the second case in the world of horizontal asymptote, and it is when the degree of the top is the same as the degree at the bottom, the same highest power. You can notice in the example in front of you that the degree is 3 in both, up and down, numerator and denominator. And in this case, your horizontal asymptote will be y equal leading coefficient of the top divided by leading coefficient at the bottom. Thus the number beside the highest power, which is 4, divided by 11. This is the rule of the second case. When you have degree top equal degree bottom, your horizontal asymptote will be always y equal LC top divided by LC bottom. Again, another example. Find the horizontal asymptote for this function. We can notice both of them, they have degree 2. Thus, immediately we will say, okay, since degree top equal degree bottom, horizontal asymptote is y equal leading coefficient top, which is 6, divided by leading coefficient bottom, which is 1. Thus, my horizontal asymptote will be equal y equal 6. Okay, the third case is when the degree of the top is greater than the degree of the bottom, as illustrated in front of you. If you have this case, there will be no problems. It means no horizontal asymptote. This section we will speak about symmetry, and there are 3 types of symmetry, and we will start with the first one, symmetric to the x-axis, and it means that the mirror will be the x-axis. Thus, if you have a shape like this where you feel that there is a mirror at the x-axis, you need to know that it's symmetric to x-axis, and the rule xy will go to x. You fix x and you change the sign of y. Thus, xy will go to x negative y. The second case, symmetric to y-axis, and you will have the mirror will be in the y-axis, and when you say symmetric to y-axis, the point xy will go to negative x y, and the mirror will be at the y-axis, and you know what? It's an even function in this case. Third type of symmetry, which is symmetric to the origin, and the point xy will go to negative x, negative y. The mirror will be at the point 0, 0 at the origin, and guess what? It's an odd function in this case. Let's start with the following example. Decide the type of symmetry in f of x equal x. Let's agree that we will call any f of x or g of x, we will say it's y. Thus the function y equal x. Now to test symmetric on x-axis, we replace the point xy by x negative y. If we replace it, we discover after simplification that y equal negative x, and it's not the original question. Thus in this case, we will say, wait, it's not symmetric on x-axis. Okay, now we have to do the same. If it's not symmetric on x-axis, we need to test if it's symmetric on y-axis or on origin. Thus we will take the point xy and we will say to test it on y-axis, xy will move to negative xy, y equal x. Now we replace x by negative x, and again it's not the original question. You're not back to y equal x, you're now y equal negative x. Thus it's not symmetric on the y-axis as well. It's not even in this case as well. Now we go to the third test, which is symmetric on origin. Thus you will take the point after that. Okay, now we decided that it's not symmetric on y-axis, not on x-axis. What is left for us? Taking the point xy and moving it to negative x, negative y, which is symmetric on origin. If you do it after simplification, you will go back to the original question. Thus, yes, it's symmetric on the origin and it's an odd function. The following example, and I want you to test the type of symmetric. First of all, let us test symmetric on x-axis. Thus the point xy will go to negative x, it will go to x negative y. Thus we start replacing y by negative y. The part with the x's, you don't change anything. Then the negative at the y side will go to the right side and it will affect the signs with the x's. Thus y will be x to the power 4 minus 4x squared minus 5, and it's not the original question, thus no symmetry on x-axis. This is number one. Now we will repeat the same step by testing the symmetric on y-axis. Thus what is the test of y-axis? The point xy will go to the point negative xy. Thus y equal, now in place of each x, we will put negative x, but please use brackets. Thus the function will be y equal negative bracket negative x to the power 4 plus 4 bracket negative x to the power 2 plus 5. Keep in mind that those brackets to the power 4 and to the power 2 are even, thus the negative will vanish. Thus the question after simplification will become y equal negative x to the power 4 plus 4x squared plus 5, and guess what? This is the original question. Thus yes, it is symmetric on y-axis, and accordingly this is an even function. As an extra work, you can do the test for the origin by replacing xy by negative x, negative y. If you do this and you simplify the whole question, you will not have, after simplification, you cannot go back to the original question. And I can assure you, this function is only symmetric on y-axis. This is an even function. It's not symmetric on 0, 0. In the coming section, we will speak about the boundedness. Think about it like boundaries. You have three types of boundedness. The first one, bounded from below or lower bound. I will illustrate it using graphs. Take the following graph in front of you. This is an example of a lower bound or bounded from below. You have in your graph absolute minimum. You cannot go below this one. Thus, any graph with an absolute minimum, it means it's a lower bound or bounded from below. Now we will go to the second type, which is bounded from above, or you have an upper bound. And let me put it like this. If you have an absolute maximum, it means it's the upper bound. Just take it like this. If you have an absolute maximum, like this case, it means that it's an upper bound. The third case, when you say it's bounded and you don't talk anymore, it means it's bounded from above and below, as it will be illustrated in this question. In this example, we will decide the type of boundedness in the following function. This is an example, or this is a graph of a reciprocal function, y equal 1 over x. You have to notice that if you go to the left side, it's bounded above. Thus we will say bounded above from the interval open negative infinity to 0 infinity to 0. This is open. Now, also we will say it's bounded from below when you go from 0 to infinity. Take another example, y equal square root of x. And this is a parent function. You need to know the graph of it. If you notice the graph, it has an absolute minimum at 0, 0. Thus it is bounded from below, but it keeps going up, thus it's not bounded from above. A third example, y equal or g of x equal x cubed. The graph will look like this. And you know what? Because it keeps going up and it keeps going down, there is no absolute maximum and no absolute minimum. It means it's not bounded. There is no boundedness in this function. Let me put it like this. In the last example, given the graph, it's easy for you to see that it's bounded from above and bounded from below as it has certain interval. And finally, when you deal y equal constant or equal number, the graph will be always a horizontal line. Thus we can say that it's the same value, the same upper bound, the same lower bound, and accordingly it's bounded because it will be that value given in the question. You can check the following question in front of you. In this section, we will cover end behavior of any graph or any function. End behavior is the description of the attitude of the graph when x goes towards infinity, negative infinity, or any other point decided by the question. In the coming example, you've been asked to find the end behavior. As an advice, use always the horizontal asymptote if you are dealing with a fraction function. Because if you go, the degree of the top is 1, the degree of the bottom is 2. We have the case degree top less than degree bottom. Thus the horizontal asymptote is y equals 0. But it is the answer of the end behavior. Thus we will say, as x goes to infinity, your y go to horizontal asymptote, which is y equals 0. As x goes to negative infinity, your y will go also to the same value of the horizontal asymptote, which is 0. For grade 12 students, they need to know how to express this one using the limit. Thus, as x goes to infinity, y goes to 0 will be written as limit f of x goes to infinity equals 0. And the same thing with negative infinity. Another example, find the end behavior for the coming g of x. You notice that the degree at the top equal 2 and the degree at the bottom equal 2. Thus we have the case degree top equal degree bottom, and accordingly your horizontal asymptote will be leading coefficient top divided by leading coefficient bottom. Thus your horizontal asymptote is y equal 3/5, and that will be the answer of the end behavior. Thus, as x goes to infinity, my y will go to 3/5, and also as x goes to negative infinity, my y will go to 3/5. A third example, f of x equal to x plus 1, and this is a line with a positive slope. Thus it's an increasing line. If you will graph it, you will discover it's a line with y-intercept equal 1, and it always increases. Anyway, any line, you cannot, let me put it like this. If you go to infinity, this is an increasing line, your line will keep going up. And if you go towards negative infinity, your line will go down. Thus we will say, as x goes to infinity, my line will continue going up. Thus my y will go to infinity. Limit f of x goes to infinity equal infinity. Now, as x goes to negative infinity, if you go to the left side and you watch your line, you will discover it's going down. Thus you will say, as x goes to infinity, my y will go to negative infinity, and accordingly limit f of x goes to negative infinity will equal negative infinity. In the graph presented in front of you, we notice at the both sides or the two hands of the graphs keeps going up. Just let me put it like this. When you go in the direction of s going to infinity, imagine yourself walking toward the infinity and you're looking at the black graph, you will notice it always goes up. Thus you will say, as x goes to infinity, I can see that the black graph goes up, thus my y will go to infinity. Accordingly, limit f of x or h of x in this case, as x goes to infinity will equal to infinity. This is a limit for grade 12 students. And even imagine yourself, you're going towards negative infinity, you're the red person now. You will notice that your function keeps going up. Up means infinity. Thus again, as x goes to infinity, y will go again to infinity. Finally, we are now by increasing and decreasing intervals. Take the following example. Decide the intervals of increasing and decreasing for the given graph. I want to highlight one thing, that if you see a horizontal line, please write it's constant. It doesn't go up, it doesn't go down. Now, I always advise my students to put their notes on the graph, like what I will do now. From negative 10 to negative 5, I will see a horizontal line. Thus, I will decide this is a constant number. Now, I have a constant, as I said. It will be followed by decreasing from negative 5 to 0, and then increasing, as you can see in front of you, from 0 to 5, followed by decreasing. Now, all what you have to do to give the answer, but the answer will be determined according to the x values. For an example, we will speak now about constant. Constant starts from negative 10 to negative 5. Again, it doesn't matter if you put the intervals open or closed, but to try to be consistent. Like we say, it's constant from close -10 to open -5. Now, followed by, or to close -5, sorry. Followed by a decreasing, which is start from open -5, because I already say it was closed. I will make it open until the value 0, and I can close the 0 value. It's okay. Okay, I want you to watch how I'm doing this in front of you. Thus, my decreasing will end by the value of 0. Okay, followed by increasing, which is from open 0, because it was already closed in the previous decreasing, open 0 until the value just before 5. No, it was actually after 5, until the value 6. I can see it from the graph now. And I will make 6 closed. Then I will say, okay, last thing is the decreasing again, but from open 6, and since it keeps going down towards x values infinity, thus it will be decreasing from 6 to infinity. Last example, again, for the given graph, decide the areas of increasing, decreasing. Again, put your notes on the graph. Thus, you can see from this direction towards number 2 on the x-axis towards the point 24, you have an increasing, followed by decreasing. And after the decreasing, you have a small increasing, followed by constant. I want you to put your notes in the exam on the graph. Then you start answering, but your answer, your starting point, your end point should be according always to the x-axis. Y doesn't have any relationship with it. Thus we will say, listen carefully or have a look carefully, just so. Okay, increasing interval will start from close 0 up to 2. Now, it's up to you. You can close 2 or open it, it doesn't matter. Now, followed by decreasing from close 2 up to the point, let me see on my, I cannot see it really clearly. Yeah, up to the point 5. Now, followed by another increasing from 5 up to 6. And then you have a constant interval that starts from 6 and it keeps going. Whenever you go to the right direction towards infinity, you will see the constant line above you. This, the constant will be from 6 to infinity. Thank you for watching.